Let the 75th Hunger Games begin.
The Hunger Games Catching Fire settles the audience into a dystopian world where Katniss Everdeen revisits the deadly arena for the Quarter Quell. Physics is featured throughout the film, from Katniss's precise archery skills to the traps demonstrating energy conversions. Furthermore, her fall from spinning cornucopia showcases concepts like relative velocity and centripetal force. Even Peeta's crash with the force field highlights the impacts of collision. Pseudo-forces come into play throughout, adding complexity to their motion, while circular motion is prevalent, increasing the action and enhancing the narrative. In this scene where we see Katniss and Peeta walking to the Panem pathway, there becomes a moment when there's a big circular turn near where President Snow stands. To find the amount of pseudo-force they feel in the turn, we must first find our period. Let's time it. Now that we've got our time, as you can see, that was only a half turn. So to solve for the period, we input the number of seconds on the top and only have 0.5 for the bottom due to only half a cycle. So we get about 26.6 seconds per cycle. Continuing on, to figure out the radius of the circle, we can approximate by using the average male height, 1.709 meters, of one of the tributes. Using the approximate height and stacking on top to the center of the circle, we get approximate radius for the circle to be around 22.22 meters. Now that we have our period and radius, we can solve for the acceleration. It can be done using these two formulas. It doesn't really matter. We just need the acceleration to plug it in for the pseudo-force formula. This is our fun little free body diagram. There's the center of rotation where the force of friction goes into. The pseudo-force will go out because that's the function of the pseudo-force. And our good old Fn and Fg, which equal to each other. Now to find our pseudo-force, we should find F net x. And our F net x is Fp minus the force of friction, which will equal to MAC. Look at that, acceleration came back, that's where we put it in. However, for our force of friction, we should assume that the coefficient of friction would be 0.6, and since the surface on the capital kinda looks dry. So our force of friction would be 0.6 multiplied by the force of normal, which is Fg. But hold on, the mass would not just be Peeta and Katniss. It would be and the chariot and the two horses. But don't worry, I got the whole mass calculated. All I need is just to multiply it by gravity. And boom, we have force of friction. Plug that back in, and here's our Fp. We just solved the pseudo-force for Peeta, Katniss, the chariot, and the two horses. Our second scene to analyze is when Peeta's heart stops. Here's where we're going to analyze the two collision, inelastic and elastic. First will be elastic since Peeta hits the force field and only he rebounced back. The force field is just chilling there. In elastic collisions, both momentum and kinetic energy are conserved. Therefore, the kinetic energy that Peeta hit with his hand would equal to the kinetic energy he flew back with. But that means we have to calculate the velocity of Peeta's hand, the displacement, and time. Here's where we're going to run into a couple assumptions. We will assume that Peeta's arm span is the same as his height, and that from finger to elbow is 1/4 of his height. So as seen from this picture here, he basically does a displacement 3/4 of his height, which I calculate to be 1.335 meters. And the time is 1 second, so that's so simple, that's the velocity. Plug that back into kinetic energy, and here's the initial velocity after Peeta hits the force field. This is where we transition into an elastic collision. We want to first figure out his impact velocity when he hits the other tributes. Timing his height, he flew for about 1.5 seconds, and we can approximate that he flew for about 3 meters. We will be using this kinematics equation, and plugging that all in, we get this impact velocity. We plug that back into our original equation, isolate for final velocity for all the tributes, including Peeta, and we get 0.881 meters per second. Here's a high-tech simulation. Peeta, no! For Katniss's bow, she has lots of powerful scenes. Found this photo online and it's a great and perfect demonstration of delta X for the spring energy and spring force. Using similar logic like I did with PETA, the arm span and the forearm being 1/4 of the height, as seen on diagram, delta X would be 42.55 centimeters approximately. However, trying to find displacement, I used multiple angles, tried measuring the steps made by the tributes on top of the cornucopia island. Katniss actually steps about 6 meters from where wires would eventually sit to the point where Katniss would shoot. So I approximated the angle and used Pythagorean theorem to find the x coordinates so that I can make a ratio. Now from the angle that she actually shoots from, I approximated it would be 30 degrees downwards. Now drawing another triangle and using sine law, I got the total displacement to be 6.7. Additionally, I'm going to add to the displacement the half of the length of the arrow. Using that new displacement, I'm going to divide it by the time that it took to hit the tribute, where we get the velocity of 32.32 meters per second. That's not all. Using this new velocity, we plug it back into the kinetic energy equation, which equals to the energy of the spring. Because remember, we haven't found spring constant yet. Making those two equal to each other, we get the spring constant of 115.47 newtons per meter. One last step. If we want to find the spring force, we multiply that new K value by the X value that we had before, which we get 49.13 newtons of spring force. And since kinetic energy equals to elastic energy, the spring energy will be 10.45 joules. Second last thing that we're going to calculate is the centripetal force of the cornucopia island spinning. The island rotates and experiences a centripetal force. As the usual step, we find the radius first. From this blurry snapshot, you can't really see, but there's Katniss right there, and we're going to use her height to find the radius. We're going to stack, multiply by the height, and we get the radius of 11.963 meters. From a different scene where Katniss already hits the water, there is a 3D model of the cornucopia spinning where you can see Katniss drowning in the water. This particular scene actually can give us the period. I observed the scene and timed it. It passed 6 of these small sections in 2 seconds. Since there's 12 sections, 6 sections is only half of it. Therefore, it passed half a cycle in 2 seconds. So the period would be 4 seconds per cycle. The usual plugging in to find the acceleration, which we get as 29.52 meters per second squared. Here's a body diagram with Katniss Everdeen, specifically her, because she is at the most edge of the cornucopia radius. Since centripetal force equals to MAC, again, here's our AC, and we will assume that Katniss's mass is 55 kilograms. Multiply those two together and you already got your centripetal force, which equals to 1,623.9 newtons. Last but not least, our beloved relative velocity. We will try to find the relative velocity of her fall into the water. Her time as soon as she hits the water is 0.5 seconds. And her horizontal velocity, as we already know, the centripetal velocity is 18.79 meters per second. That will be our velocity x component. Now for the y, we're going to use actually gravitational acceleration. Since acceleration is velocity over time, we can find the velocity in the y direction using this. And it will be 4.905 meters per second downward. We add those two vectors by using Pythagorean theorem, and we get the relative velocity at 19.42 meters per second. This is her impact velocity onto the water. This project has delved deeply into the fascinating connections between physics and the cinematic world of The Hunger Games: Catching Fire. By analyzing key scenes, we explored fundamental physics concepts such as energy conversions, elastic and inelastic collisions, centripetal force, and pseudo-forces. Katniss's archery skills demonstrated the principles of spring and elastic energy, while Peeta's collisions with the force field highlighted the conservation of momentum in collisions. The spinning cornucopia island scene illustrated the effects of centripetal force and relative velocity, adding a dynamic layer to the characters' experiences. This analysis underscores how physics not only enhances the narrative but also provides a richer understanding of the characters' actions and the challenges they face. Overall, this movie showcases the critical role that physics principles play in crafting compelling and believable stories, particularly in a complex and action-packed film like Catching Fire.